how light interacts with different materials. So we're going to talk about is what happens when light hits different types of materials, whether it's glass, whether it's concrete, whether it's tinted glass. We're going to discuss how light interacts with those materials and then what you would see if those materials get hit by light. So we're going to first talk about emission. Emission is there's two types of emission. There's black body emission. When you have something at a very high temperature, usually around 1,000 Kelvin, they release a spectrum of colors. In this situation, you can see it's a reddish-orange color, orangish color, and this is just intense yellow, or if you want to call it even white, light out of it. And the reason these things are releasing energy is because you're heating them up to such a high energy that's releasing light. So black body emission is a fancy way of saying that the object is so hot that it emits light. So it's emitting light only because of the heat that the object is experiencing. The other type of emission is spectral emission. Spectral emission is basically what happens when you put energy into an atom or element. And each element has a very unique pattern of colors produced. This is hydrogen. So hydrogen produces these 4 bands. Only hydrogen produces these specific 4 bands. It's like a fingerprint for an element. Spectral emission allows us to identify an element, so we could tell what's in the sun and the stars based on their spectral emissions. And once again, the result is that energy is put into these atoms or elements inside the substance, and it's causing the electrons to jump to higher shells, and it comes back down. It produces very specific color patterns, and then you can use those in turn to identify it. So that's the emission version of what happens in terms of light. And one of the interactions would matter. One is black body, where it emits light itself. The other is resulting when you put energy into an atom or element to produce a very specific pattern of colors, which you can in turn use to identify that element. Absorption is when matter absorbs heat. So easy way to look at this is like, for example, if you're walking on a hot day on sand or concrete, you will experience heat coming from those objects. And the reason is that light is hitting those objects and it's being absorbed by them. So when an object absorbs light, it in turn increases in temperature, and you would experience that temperature change if you make contact with that item. Transmission, some matter like glass, actually allows light to pass through. So here you can see what's going on is that the way the material is made, light is able to go straight through these glasses, and as a result, you're able to see what's on the other side of it. Reflection, on the other hand, is photons bouncing off the surface of some matter, like a mirror. Here's a pretty example of that. So you can see it's a mirror image down here. You have the tree, and everything's being reflected by the water. So water could actually reflect light. It could also absorb light, as you're probably all aware, because the swimming pool, as you progress into summer, into deeper parts of summer, it gets hotter and hotter. We shouldn't say hot, it gets warmer. That's because it's absorbing energy from the sun, and that's increasing in temperature. So here's an example of transparency, translucence, and opaque materials. So if you have a transparent material, which is what you usually associate with glass, light will go straight through it. And you can see all these waves of light that are hitting on this side are in turn going straight through to the other side. On this example, on the other hand, you can see what's going on is that you have a lot more going in than is going on the other side. So a lot of this light is being blocked. And that's what tinted glass does. That's what translucent material does. It prevents some of the light from going through. You could still see the image of the cow, obviously, but not to the same extent you could with the glass. Opaque, on the other hand, you can't see anything. It's completely blocked from your vision. So you're basically blocking the view altogether. All the light hits it, nothing goes through. You're not able to see anything. You can't see the cow anymore. So examples of light, here's some visual different variations of it. So you have the light bulb emitting light, so this is going to be black body emission. It's being reflected off of this mirror, being absorbed by this chair. So the light, if you don't have LEDs, if you have the old-fashioned incandescent light bulbs, it actually does generate heat. So it would make things around it a little bit warmer. And that's what's happening here. The chair is absorbing that energy. You have transmission of light through here. So light from the outside is able to go through, and you're able to see outside and see everything outside of it. Your blue shirt absorbs all the colors except blue. In case you know how color absorption or why you see different colors, how it works, this is the way it works. Light hits this. So the light has basically Roy G. Biv, all the colors of the spectrum. And what happens is that all these colors are absorbed except for the color you see. So here you're seeing blue, so that means Roy G. and violet is being absorbed, and what you're seeing is the blue. So blue is reflected out. That's how it works. So when you get a white light, has the full spectrum of colors, all 5 of these, excuse me, 6 of these. And what happens is whatever color you see, it's absorbing all the colors except the one that gets reflected back, and that's what you're seeing visually. That's what's happening with the red chair as well. It's absorbing everything except red. Red's the ones reflected. Snow is also reflecting light here. The ground's absorbing energy, so on and so forth. So white reflects all visible light, while black absorbs all light. In case you didn't know, this is the reason why you want to wear a white shirt on a hot day, not a black shirt. White light reflects, or white shirt reflects most of the colors of the spectrum, so you get very little heat from the light that's hitting you. You still get it from UV, but you won't get it from the visible light. Whereas if you wear black, all those colors are absorbed in addition to UV, so you're going to feel a lot warmer. It's not like white's going to make you completely cool on a hot day, but it'll make you cooler. Here's an emission spectrum versus continuous spectrum. The difference here is that an emission spectrum has a sequence of colors. You can see how they're separated into 4 different bands. The continuous spectrum doesn't do that. It's all the colors of the rainbow, Roy G. Biv, from 350 all the way to 800. That's all the wavelengths for colored light. In case you're wondering, you can see violet is going to have the shortest wavelength and the highest energy at 350 nanometers, and red is going to have the longest wavelength and shortest energy, or weakest energy. That's the way the continuous spectrum works. So when energy is put into and causes electrons to jump to higher levels, you get the color spectrum or the emission spectrum as you're seeing here. So everything has a very unique pattern based on what element it is. Continuous, on the other hand, produced by hot objects like the sun, volcanic lava, incandescent light bulbs, and shows full spectrum. So light we get from the sun, light we get from incandescent light bulbs, and if you ever go to a volcano, those are all going to have continuous spectrum. See all the colors of the spectrum from it. Not just these 4 little bands you would for the emission spectrum. The other thing you want to note is that hot objects show more green, blue, and violet, while cool objects show red and yellow. So if you see a black body emission and you see more of a red or yellow, that's not high as temperature. If you see green, blue, and violet, it's extremely high temperature. So you can actually kind of tell how hot the object is to some level of accuracy based on the color you're seeing as well. Here's the atomic spectrum of noble gases. This is what you would see if you're doing it in a classroom. These are spectrum tubes, and this is helium. So you heat up helium, and it's the color spectrum you would see in class or visually, based on the fact that this is the color pattern produced by neon. It's got a really pretty one. Argon, a little bit more pronounced. So each of these are unique. You can see neon and argon and helium are all different. So that's where we can use this to just identify the elements. Here's the different spectrums again. You can see this is a continuous spectrum. You can see this is for specific elements. This is sunlight, by the way, the top one. Hydrogen, specific pattern. Helium, specific pattern. Mercury, uranium. They all have specific patterns. And the more electrons they have, the more interesting the pattern. Because you could look at hydrogen, only has 4 bands. But helium has 1, 2, 3, 4, 6, 7 bands. 7 bands. And then it just increases, you have more electrons. All right, let's look at the emission spectrum. The emission spectrum that serves as fingerprints for an element caused by electrons moving from one energy level to another, result of energy input. That's a fancy way of saying that when you have an atom, you have shells. So we're going to show our shells this way instead of showing them in circular form. So what happens is that when these electrons in these shells jump to a higher shell, as a result of energy input, they come back down, they produce colors. And based on how many electrons you have in the element, it produces a different number of bands. Now, hydrogen only has 1 electron, but if you notice from that diagram earlier, it had 4 bands. So it means the hydrogen jumps from the first to the second, first to the third, first to the fourth, so on and so forth. And it has a total of 4 different jumps at 1 electron. So it doesn't tell you how many electrons an element has based on the bands. It just tells you basically that, what the identity is, and that's as far as you can go with it. After electrons jump to higher energy levels, they come back down and produce color, and that's what you're going to see visually. So let's take a look at these energy levels to understand this a little bit better. So first thing you need to understand, when electrons are in their normal energy levels, they're said to be the ground state. So if you don't put energy into an electron, they're in the ground state. That's the normal location for that electron, for that element. So for example, hydrogen has one electron, it's going to be in the first shell. That's it. Helium has two, it's going to have two in the first shell. That's it. Lithium is going to have two in the first shell, one in the next shell. It keeps on going as you add more electrons. That's the ground state. When energy is put in and causes an electron to jump to a higher shell, you say it's excited. So what does that look like? Let's say you have carbon. Actually, carbon's too much. Let's go lithium. So you have a total of 2 electrons in that first shell. So we're going to represent it by these little funny-looking bars. And you have 1 in the next shell. So excited state means basically that, let's say you have a third shell up here. One of these electrons in this shell jumps up there, and it's located there temporarily. It's excited state. It's just correct number of electrons, but now jump to another energy level. That's what excited state basically means. It just means that the electron is taken from where it was and put in a higher shell level. It eventually will come back down. When an electron in an excited state returns to lower energy level, it emits a photon. What's a photon? Color. Fancy way of saying color. So when this comes back down, maybe you see a red color, maybe you'll see blue, whatever. Depends on how far it went. The further it goes, the more energetic the color. And as we said before, your colors go from red being the lowest energy all the way to violet being the highest energy. All right, so let's take a look at these energy levels more closely. You have, in this situation, 5 shells. You can see it's increasing energy. So the 5th shell has more energy than the first shell. Kind of like looking at if you were living in this building, where would it hurt more if you jumped off of the 5th floor or the 1st floor? Answer, obviously, the 5th floor, and if I was wondering why, because as you go up to the 5th floor, you're storing energy. And when you come back down and try to jump, you're going to transfer all the energy you just stored by getting to the 5th floor down into the ground. The ground's not going to want it. So here you take us back, and boom, you get hit with that energy, and you get hurt. So electrons, the further they are, the more energy they have. That's the long and short of it. There's 7 possible energy levels because there's 7 technical periods in the periodic table. Based on what we've discovered, theoretically, you could have an infinite number of shells, but for our purposes, 7 is the limit. The further electrons from the nucleus, the more energy it has. So that electron, that 5th shell, has more energy than an electron in the 2nd and 3rd shell, for example. Production of color. So what happens? Energy is put in, an electron jumps to a higher shell. So what you're seeing here, you put energy in, and let's say for this situation, you cause it to jump from the first, let's go over here to this right side, excuse me, left side. So this electron went from the first shell to the 2nd shell. So what color did it produce? Well, it doesn't really show you in this particular example what these ones over here produce, so it's going to ignore these. So we're going to look at these ones. All right, so let's take a look at this one. This one from the 2nd shell to the 3rd shell came back down. So what does it produce? Red. Only 1 shell increase, so it's a low energy color you're going to see. Next one, you're going from the 2nd shell to the 4th shell. Look at the color, green. Remember Roy G. Biv in terms of energy? So green is pretty energetic. So going from the 2nd shell to the 4th shell, 5th shell, my apologies. For this one it's 5th shell, for this one it's the 4th shell. Let's label this so you can see this a little bit better. So going to the 4th shell produces green. If you go to the 5th shell and come back down, you actually produce a bluish color. That's really energetic. So it doesn't mean you're going from the 1st to the 7th shell exactly that you're producing all the energy. It could be a very small increased number of shells. Just look at this. You went from 2nd to 3rd, produce red, but when you go from 2nd to 4th, you produce green. You completely skipped orange and yellow. Anyway, that's how the color bands are produced, is based on these electrons coming back down to the original location, and that's what we use to identify the elements. So when it drops back down, it produces color. Distance electron drops determines the color. So obviously, the more energetic, the further it went. So Roy G. Biv, the color spectrum red, orange, yellow, green, blue, and violet are colors produced as a result of electron movement. We talked about that. Red has the lowest energy and the longest wavelength, while violet has the most energy and the shortest wavelength. This is why red lasers are usually less deadly compared to green lasers. And the reason they're less deadly is because they're less energetic. So getting hit by a green laser is going to be much more painful than red. And easy way to look at this, when they do like eye surgery, they use the more energetic colors like blue and violet. to do that kind of surgery, because that basically eats up or tears up tissue around your eyes, and that requires a high energy. Each element produces a unique set of these colors, which can be used to identify the element. That's what the emission spectrum is. All right, energy levels. You can see this is going from this shell to this shell. It's not much of a jump. Over here, going from here to here. Produces an orange color, low energy. This one a little further based on distance. Look at this, how far this went compared to this. It produces green and more energetic color. Here's another example. Went up one shell, red. Went up, looks like two shells, but look at the distance once again. It's not the number of shells or how far it's going that matters. And that produces blue. Flame test, we could also identify elements with this. It's another way of identifying them. Besides the emission spectrum, specific elements have specific colors. So when you see this reddish color, that's going to be a lithium. If you see an orangish color, if you put, so what they basically do is take a sample of the element, they put it onto this nichrome wire, put it into a Bunsen burner, you see colors. And that color helps you identify the elements. You can actually identify an element this way. Potassium produces a bluish color, calcium orangish, and strontium looks like a violet color or magenta. That's how we identify elements as well. It's not as accurate as the emission spectrum, but it's another option. And in case you're wondering why it's that important, fireworks. When you see fireworks, what you're basically seeing is the elements inside them exploding. So when you see this reddish color here, it's probably lithium that they have as the base for that. So they put energy in the form of gunpowder, blow it up, and then when the electron jumps, comes back down, produces a reddish color because it's lithium. Orange, obviously more energetic. Violet is going to be the most energetic out of all these, right? So having an element that produces that, and each firework has a very specific element that's inside of it that makes up that particular element. All right, so let's try some questions. In each of the following energy level changes, indicate if the energy is absorbed or emitted or not changed. Electron moves from the first shell to the third shell. It's going up. Anytime you're going up, you're absorbing energy. Anytime you're coming down, you're producing energy or releasing energy. Electron falls from the third to the second shell, it's coming down, so that's going to be obviously going to be emitted. Electron moves within the third energy level. Within is nothing, right? It's negligible. There's no change in energy. All right, out of RGB, which color would have the shortest wavelength? Well, shortest wavelength would be the highest energy. That should be violet. Out of RGB, which color would have the highest frequency? Still violet, because that's going to have the shortest wavelength. Remember, there's an inverse relation between wavelength and frequency. The shorter the wavelength, the higher the frequency, and vice versa. All right, last thing we're going to go over is how to use emission spectrum to identify elements. So here's an emission spectrum for D. This is for E. This is for G. So there's a color pattern produced for each of these. And what I want to know is which elements are used to make up this. So how do I do that? So the way you do it, you line up. So you see how this one has this right here, and that lines up with this. So D is definitely in it. G definitely is not. Why? Because if G was in it, this mixture, the way this works, if you make a mixture of different elements, it should produce an identical set of patterns inside this image for the mixture. So if you miss a band, that means that element's not there. So G doesn't have this, doesn't have this either. Either way, G's not in it. So D definitely is. Question is E in it? Well, you see how there's a pattern right there. See right there. Matches up, right? So D is in it as well. And here's E right there, there, and you can see right there, there, and there. So the elements that make up this particular substance are going to be D and E, which is going to be the first one. And that's how you use the emission spectrum data to identify what elements in the mixture. So I would, for example, give you this mixture, give you these, and all you have to do is just line it up like I just did and say, okay, well, it's got to be this element or that element. So this is how matter or light interacts with different forms of matter.